Good morning to all. In the previous class, we are discussing about green chemistry. Then today's topic is reactions. So here, in this pericyclic reactions, we are discussing about which are called as pericyclic reactions and what is the classification of pericyclic reactions and what is HOMO, what is LUMO, how we can explain the symmetry for these complexes. Okay, so today we are discussing about reaction. The first one is about what is the definition of pericyclic reactions. The reactions which are concerted reactions. The reaction which are concerted reactions taking place through the cyclic transition state, that is cyclic rearrangement of electrons. It involves in the transformation of one molecule to another molecule, another new molecule, without involving ionic radial intermediates. It is called as pericyclic reaction. Okay, once I repeat. So, which are called as pericyclic reactions? So, in this, these are the concerted reactions. In this, by taking the cyclic transition state only, a new molecule is produced. In this formation of the molecule or formation of the products, we could not use any intermediate radicals or ions. Then what is the features of these pericyclic reactions? So these reactions are reversible, induced by heat or light by highly stereospecific. Okay, once I repeat. So these reactions are reversible reactions and these reactions are induced in the presence of the heat or light. We could not use any solvent. So that's why it is also called as green synthesis reaction. These reactions do not involve a reactive intermediate like carbocation, carbanion or free radical. Understood? So in this reaction, no intermediate or carbocation or carbanion is not involved. Only direct the reactants are converted to product in the presence of the heat or light. So those reactions are called as pericyclic reactions. However, a reactive intermediate may undergo pericyclic reaction. So these pericyclic reactions are largely unaffected by the catalyst or solvent polarity. That means, so by formation of a product, in this pericyclic reaction, we could not use a catalyst or a solvent. Then the next one is classification of pericyclic reactions. These pericyclic reactions are classified into mainly three types. Number one is electrocyclic reactions. Number two is cycloaddition reactions. Number three is sigmatropic rearrangement reaction. Once I repeat. So pericyclic reactions are classified into three types. Electrocyclic reactions, cycloaddition reaction, sigmatropic rearrangement reaction. So first we are discussing about the electrocyclic reactions. So which are called as electrocyclic reaction. An electrocyclic reaction may be defined as formation of a sigma bond between the terminal termini of a conjugated pi system are the reverse process. We can take in this electrocyclic reactions, the pi bond rearrangement should be takes place and a sigma bond is produced. And by using that sigma bond, the two carbon atoms get the sigma bond and it is formed as a cyclic structure. Let us take this example. It is 1,3-butadiene. So in this 1,3-butadiene, in the electrocyclic reaction, it is converted to cyclobutene. Let us take how this is the reaction. Let us take the mechanism. We can take the cyclo 1,3-butadiene like this. This is 1,3-butadiene. This is the first carbon. This is the second carbon. This is the third carbon. This is the fourth carbon. Okay. So in this, in the presence of heat or sunlight, here, so these pi bonded electrons are shifted here. Then this carbon get the positive charge. Once I repeat it, wait a minute. Okay, these pi bonded electrons are shifted here. Then the next pi bonded, the third carbon and fourth carbon pi bonded electrons are shifted over here. Then it is converted to like this. So these pi bonded electrons are shifted here. Then this carbon get the positive charge. Then the pi bonded electrons are shifted here. Then these electrons, pi bonded electrons are shifted here. Then this carbon get the negative charge. So this carbocation donate the electrons to this carbon ion donate the electrons to carbocation and take a sigma bond in between these two carbons. So this is the first carbon. This is the second carbon, this is the third carbon, this is the fourth carbon. So 1 and 4 carbons produce a sigma bond. So this type of reaction is called as electrocyclic reaction. Okay. Then look at this. The forward reaction in which the forward reaction in which the 4 pi electron participate is called electrocyclic ring closure of 4n pi electron system. The reverse reaction in which 2 pi electrons and 2 sigma bonds electrons participated is called electrocyclic ring opening of 4n electron system. So here in this 1,3-butadiene, totally 4 pi bonded electrons are present. So that's why it obey the 4n pi electron system, because if n is equal to 1, then 4 into 1 is equal to 4. Okay. So here totally 4 pi bonded electrons are present. So that's why it obeys the 4n pi electron system. Due to the 4n pi electron system only, it undergoes the electrocyclic reaction. Let us take the next example. So let us take this another example, that is 135 hexatriene. We can take this one. So this is called as 135 hexatriene. So this 135 hexatriene, it is converted to, wait. So this is called as 135 cyclohexatriene. Sorry, 135 hexatriene, because it is in this 1, 2, 3, 4, 5, 6 carbons are present and 3 pi bonds are present. Okay. So in this structure, totally 6 pi bonds and 6 carbon atoms, 3 pi bonds are present. So that's why it is called as 135 hexatriene, or it is mentioned as hexa 135 triene. In the presence of the heat or sunlight, it is converted to cyclohexa 1,3-diene. So here we can take this structure like this. Let us take, this is the first carbon, this is the second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. Okay. Then first carbon is having the double bond. Then third carbon is having the double bond. Then fifth carbon is having the double bond. Here, what happens in the presence of the sunlight? So this pi bonded electron, the 1, 2 carbons pi bonded electrons are shifted in between the 2 and 3 carbon atoms. Then after, the 3, 4 carbon atoms pi bonded electrons are shifted over to 4 and 5 carbon atoms. Then the 5 and 6 carbon atoms are shifted to here. Then after, it is converted to this type of structure. So 1, 2 carbon pi bonded, 1, 2 carbons pi bonded electrons are shifted over to 3 and 2 and 3 carbons. Then the 3, 4 pi bonded electrons are shifted to 4, 5 carbons. Then the 5, 6 carbons, this is shifted to here. Then it takes the positive charge. So in this process, this carbon can donate the electrons to this carbocation. And the sixth carbon and the first carbon get the sigma bond. Sorry. Okay. So this is the sixth carbon. This is the first carbon. It get the sigma bond. So this is example for 4n plus 2 pi electron system. This is example for 4n plus 2 pi electron system. In this, the total number of pi bonded electrons are 6. So that's why it obeys the 4n plus 2 pi electron system. Okay. So here take another example. So in this also, so this an allyl carbocation, it is also produced, it is converted to a cyclopropenyl carbocation. Okay. So this type of system, in this, the number of pi bonded electrons are 2. So that's why it does not obey the 4n plus 2 pi electron system or 4n electron system. So that's why n is equal to 0. Then the next type of reactions are cycloaddition reactions. So which are called as cycloaddition reaction. So a cycloaddition reaction may be defined as an addition reaction between the two or more pi systems to form a cyclic adduct, or the reverse process. Once I repeat, a cycloaddition reaction may be defined as an addition reaction between the two or more pi systems and form a cyclic adduct. That means in this reaction we can take the pi systems, two pi systems. So these two pi systems are combined with each other by using the pi bonded electrons and produce a cyclic structure. Let us take this one, that is, we can take the alkene. Okay, so in this alkene, so these electrons are shifted over here. Okay, these electrons are shifted. Let us write. Wait a minute. So I can write this like, this is the first carbon, this is the second carbon. In this also, okay, this is the 1, 2, then we number like this is 1 and this is 2. Okay, so here what happens, these pi bonded electrons are shifted to second carbon. Okay, then it is converted to like this. The second carbon is acting as the electron rich center and first carbon is having the positive charge. Okay, then next here also double bond is present. Then these pi bonded electrons are shifted toward the second carbon. Then it is converted to like this. So here the pi bonded electrons are shifted toward the second carbon and first carbon gets the positive charge. Okay, then here in this structure, okay, in this structure, it is having the negative charge. In this structure, it is having the positive charge. So these electrons are shifted over here. In this, it is having the negative charge and it is having the positive charge. So these electrons are shifted over here. Then after, it is converted to a cyclic structure like this. Okay, so this is in this process we can take the 2 pi electron system. This is one pi electron system. This is the another pi electron system. These two pi systems are involved in the addition and produce a new product or a new molecule. So that type of reaction is called as cycloaddition reaction. And in this molecule, let us take so it is also called as 2 plus 2 addition, because so here 2 pi bonded electrons are present, here also 2 pi bonded electrons are present. So that's why it is also mentioned as 2+2 cycloaddition. Then next, take this complex. So this is 1,3-butadiene. Wait. So this is 1,3-butadiene. It is reacted with olefin or ethylene. Then it is converted to cyclohexene in the presence of the heat or sunlight. It is called as 4+2 addition because in 1,3-butadiene, 2 pi bonds are present. 2 pi bonds are nothing but 4 pi bonded electrons. Okay. In ethylene structure, only 1 pi bond is present. That means 2 pi electrons are present. So that's why it is mentioned as 4+2 pi electron system. It is called as 4+2 addition. Okay. So how this reaction takes place? Let us take this is cyclobutadiene. Okay. It is reacted with the alkene or olefin. This one is called as, it is called as dienophile. So in this reaction, these electrons are shifted here. Then these electrons are shifted here. Then these electrons are shifted here. At that moment, let us take explain like this one. This one. Wait. Okay. So these electrons are shifted here and these electrons are shifted to this carbon. Then this is having the pi bond. These electrons are shifted to this carbon. Then what happens? Let's see. So these electrons, these pi bonded electrons are shifted here. Then this carbon get the positive charge. And the second and third carbon get the double bond. Then the third and fourth carbons, pi bonded electrons are shifted toward the fourth carbon. Then it get the negative charge. Okay. Then it is reacted with the olefin. So these pi bonded electrons, so it is like this CH2, CH2. Okay. So these electrons are shifted over here. Then it get the negative charge, it get the positive charge. So these negative charged electrons are shifted over here and these negative charged electrons are shifted over here. Then it produces a cyclic ring like this. It is called as cyclohexene. Okay. So you could not get any confused that it is directly 1,3-butadiene. It is itself involved in the reaction. It produces a cyclobutene. Let's look at this. So in this structure, we can take only 1,3-butadiene. It is involved in the itself only produce the product, then it is called as electrocyclic reaction. If we can take the 2 pi bonded systems, okay, in this we can take the 2 pi bonded system and 2 pi bonded systems are involved in the addition. That's why it is called as cycloaddition reaction. Then this is another example. So it is called as narborane diene. So it is having the 2 pi bonds and it is reacted with a alkene, produce this type of structure. So here it is called as 2+2+2 addition, cycloaddition reaction, because in this it is having the 2 pi bonds. It is also having 2 pi bonds. It is also having 2 pi bonds. The next type of reactions are sigmatropic reactions. So which are called as sigmatropic reactions? Let us see. These are also known as sigmatropic rearrangement reactions. Rearrangement reactions అని కూడా అనొచ్చు. ఎందుకంటే because of migrate of the one atom, it takes place in this reaction. So in these reactions, an atom, that is hydrogen or a group, migrates with its sigma bond and form a alpha position of a double bond. Okay. To a new position in the system, in the pi system. The sigmatropic reactions are classified as IJ shift or shift of order IJ. IJ is nothing but the atom is migrated from one place to another place. So which place to which place it is shifted. So that is called as IJ shift. So which reactions are called as sigmatropic reaction? The sigmatropic reactions are also called as sigmatropic rearrangement reaction. So in these reactions, an atom or a group migrate with its sigma bond to the pi bond position. That type of reactions are called as sigmatropic rearrangement reaction. Let us take this example. So in this example, already it mentioned the first carbon, second carbon, third carbon, fourth carbon, and fifth carbon. Okay, and the pi bonds are in between the fifth and 4 is pi bond is present. Then 3 and 2 are also having pi bond. Here what happens? In this reaction, the first carbon hydrogen atom, it is shifted toward the fifth carbon, and the 5 and 4 pi bonded electrons are shifted toward the 4 and 3 carbons. Alternately, the 3 2 pi bonded electrons are shifted over to 1 and 2 carbons. Okay, so in this reaction, the shifting takes place from the first carbon to fifth carbon. The first carbon hydrogen is migrate to fifth carbon. So that's why it is called as 1,5 shift. As well as the fourth and fifth carbons pi bonded electrons are shifted over to third and fourth carbon atoms. Okay. So two types of rearrangements are takes place. One is pi bond is shifted. Another one is the atom also migrate from one place to another place by taking its sigma bond. So this type of reactions are called as sigmatropic rearrangement reactions. Then in this topic, the topic is about, we are discussing about conrotatory complex compounds and disrotatory electrocyclic reactions are present. So which reactions are called as conrotatory and which reactions are called as disrotatory electrocyclic reactions? Let us take this one first. First, we are know what is conrotation and what is disrotation. So here, look at this. So this, if the rotation from this, if the rotation of the two p orbitals is in the same direction, okay, the rotation of the p orbitals in the same direction, that means it may be the clockwise direction or it may be the anti-clockwise direction. So the cyclic cyclization is called as conrotatory antam. Okay, na? Or it is called as con electrocyclization. Once I repeat, the rotation of the p orbitals in the same direction, that is in clockwise direction or anti-clockwise direction, that rotation is called as conrotatory. If one, suppose two p orbitals are there, in these two p orbitals, the rotation takes place in the opposite direction. That means one p orbital is rotated in the clockwise direction, another p orbital is rotated in the anti-clockwise direction. That is called as disrotatory, or it is called as diselectrocyclization. Okay, what is conrotatory? The two p orbitals are rotate in the same direction, that is clockwise or anti-clockwise. It is called as conrotation. If the two p orbitals are rotate in opposite direction, one is rotated in the clockwise direction, another is rotated in anti-clockwise direction, that is called as disrotatory, or it is called as the diselectrocyclization. Let us see example. Here already we know about 1,3-butadiene. So it is learned in the electrocyclic reaction. So here 1,3-butadiene in the conrotation or in the disrotation, it is converted to cyclobutene. Here look at take. So here two pi bonds are there, two pi bonds. It is nothing but totally 4 p orbitals are present. Okay. So look, let us take. So these are the 4 p orbitals. So these 4 p orbitals, these dumbbell shaped orbitals can take the rotation. It is this also move in clockwise direction and it is also moving clockwise direction. Wait. So here let us see. Let us take. So here this p orbital is rotated like this and this p orbital is rotated like this and produce a sigma bond. So that's why it is called as conrotatory. This is the another one. Here in this reaction, so this is move in the clockwise direction. So this p orbital can rotate in the clockwise direction and this p orbital is rotate in the anti-clockwise direction but produce the sigma bond. So this type of complex is called as disrotatory complex and the previous complex is called as conrotatory complex. Okay. Then take the another examples. So look at this. So here we can take the 2,4-hexadiene. So this is the structure of 2,4-hexadiene. This is the structure of 2,4-hexadiene. Okay. So in this, it produce the, it is involved in the conrotatory as well as disrotatory. When it is involved in the conrotatory, it produces the trans product. When it is involved in the disrotatory, it produces the trans product. Okay. Suppose we can take this 2,4-hexadiene. In this 2,4-hexadiene, this p orbital can move in the conrotatory. This also move in the conrotatory. Then it produces a complex. So this complex is in the trans position. If we can take this in the disrotatory, so it is moving the clock and it is moving the anti-clock, then produce the product. But the methyl group's positions are same. So that's why it produces the cis product. Wait a minute. Here, so this methyl group is toward the upward position, it is toward the down. So these two are opposite to each other. So that's why in con rotation, it produces the trans product. In cis rotation, it is toward the above the plane. It is also toward the above the plane. So that's why it is called as cis product. And in the dis rotation, it produces the cis product. In the con rotation, it produces the trans product because one methyl group is present at the above the plane, one methyl group is present at the below the plane. So that's why it is called as a trans. That means in con rotation, it produces the trans product. In dis rotation, it produces the cis products. Then next topic is about, we are discussing about suprafacial and anterafacial. So which one is called as suprafacial and which one is called as anterafacial? Look at this. Addition to a pi system can take place in two ways. Addition may be on the same face. The addition may be on the same face is called as suprafacial. Okay. And addition may be on the face of pi system, the opposite faces. Okay. Addition may be on the same face of the pi system. It is called as suprafacial. The addition may be takes place on the opposite faces. It is called as anterafacial. Let us take which is suprafacial and which is anterafacial. Here in this, so the addition may be takes place on the same face. So here the addition is takes place at the same face. Okay. So that's why it is called as suprafacial molecule. If one is in the upward and another one in the down position, then that means it in these opposite faces are there. Okay, the addition takes place in between the opposite position. It is called as anterafacial. If the addition maybe takes place in the same face, it is called as suprafacial. So that's why the cis takes place as the suprafacial because the same face addition should be takes place. This is called as anterafacial. One is the above face and another one is the below face. So this is called as anterafacial. And these are the some of the examples of suprafacial as well as anterafacial. So these examples. So these are also some of the examples of suprafacial as well as anterafacial. The next one is about molecular orbital and symmetry property. So before knowing about the molecular orbitals, we can know about some of the words. So which are called as molecular orbitals and which are called as what is LCAO, what is MO, what is HOMO, what is LUMO. Okay. So here the linear combination of atomic orbitals can generate the molecular orbitals. That means, so it is the linear combination of atomic orbitals are converted to molecular orbitals. Okay, the atomic orbitals are converted to molecular orbitals. So in this molecular orbitals, three types of orbitals are present. One is bonding molecular orbitals. Okay. Next one is anti-bonding molecular orbitals. Number three is non-bonding molecular orbitals. Okay. The LCAO is converted to molecular orbital. Then in this bonding, the molecular orbitals are three types. Bonding molecular orbitals, anti-bonding molecular orbitals, as well as the non-bonding molecular orbitals. Okay. And the lower energy orbitals are called as bonding molecular orbitals, and the higher energy orbitals are called as anti-bonding molecular orbitals. Okay. So here, if the why in some conditions, if the linear combination of atomic orbitals, the atomic orbitals are, if this is equals to n is equals to 4, 6 like this, okay, then they can produce the bonding, same number of bonding and anti-bonding molecular orbitals if the n value is equals 1, 3, 5. Okay. So like this, then they produce the bonding molecular orbitals, anti-bonding molecular orbitals, as well as non-bonding molecular orbitals. And these bonding, anti-bonding, non-bonding orbitals, they are mentioned in these pericyclic reactions like Psi1, Psi2, Psi3, Psi4. Okay. So Psi1, Psi2, these are called as bonding molecular orbitals, and these two are called as anti-bonding molecular orbitals. So in this, we can explain the symmetry, okay, as well as anti-symmetry also. The symmetry is explained by the symbol of S, and the anti-symmetry it is explained by the symbol of A. Okay. And these orbitals are having the mirror plane, that is symmetry, and these are some are having the two-fold rotation axis of symmetry, that is called as C2 axis of symmetry also produced. Let us take in this one example, that is 1,3-butadiene. So this is the 1,3-butadiene molecular orbital diagram. So in this 1,3-butadiene, totally 4 pi-bonded electrons are present. So these 4 p orbitals are involved in the linear combination of atomic orbitals. Then they are converted to 4 molecular orbitals. So these are mentioned as Psi1, Psi2, Psi3, Psi4. Psi1, Psi1, Psi2, Psi3, as well as Psi4. Okay. So this is about the MOT diagram of 1,3-butadiene. Okay. Molecular orbital diagram of 1,3-butadiene in pericyclic reaction. So in this, let us take, this is molecular orbitals. Then this is the designation. Designation is Psi1, Psi2, Psi3, Psi4. And Psi1, Psi2 is called as bonding molecular orbitals. Psi3, Psi4 are called as anti-bonding orbitals. Then number of nodes. So I can explain what is a node. Node is nothing but electron probability is zero. That means the electron finding is zero. That is called as number of nodes. How we can know the nodes? Let us take. So in this, the positive, so here the symbols, suppose we can take some are having the dotted and some orbit is meant like this. Once look at this. So some are like this one, some are like empty. So this is indication as one are having the positive sign, another is having the negative sign. Okay. So look at this. So in this bonding, in this molecular orbitals, wait a minute. Suppose we can take the shaded line is positive charge, positive node. If the empty place is indication of negative, then here look at this in this system. So there is only same charge particles are present. So that's why here the nodal value is equals 0. So in this, this is the, suppose this is the plus symbol, this is the minus. It is denoted like minus and this is denoted like plus. So here the electron probability is 0. So that's why it is the node is 1. Here by this is the one node, this is the another node. So electron probability is 0. So that's why it is the two nodes are present, it is 2. So in this is one node, this is one node, this is another node. So the node value is equals here 3. So from this we can find out the nodes. Okay. The next is about symmetries. So here Psi1 is having the symmetry. So that's why it is denoted by yes. Okay. The next, this Psi2 is having the anti-symmetry. It is indicated by A. And Psi3 also having the symmetry. So that's why it is also mentioned as S. And Psi3 also mentioned as anti-symmetry. And in this, the Psi4 as well as the Psi2 are having the C2 axis of symmetry, and the Psi3 and Psi1 is having the or doesn't having the C2 axis of symmetry. So it is mentioned as A. So this is about the a small discussion of the molecular or orbital diagram of the 1,3-butadiene in this pericyclic reaction. Okay. And these are some of the examples. So this is another example. So these are the some of the examples of this one. So up to this, the chapter is completed. Let us take a brief discussion. In this pericyclic reactions, we are discussing about the types of pericyclic reactions. The pericyclic reactions are three types. One is electrocyclic reaction. Number 2 is cycloaddition reaction. Number 3 is sigmatropic rearrangement reaction. Okay. The next we are discussing about what is Kahn rotation and what is cis rotation. So in Kahn rotation, trans product is produced. In this rotation, cis product is produced. Okay. Then in this we are discussing about anterafacial and suprafacial. Okay. Then discussing about the molecular orbital diagram. So in that we are discussing about the and as well as the some examples. Okay. So this chapter is finished. Okay. Thank you.